colligative properties. The colligative properties mean that is already we learned that is vapor pressure of a solution decreases when a non-volatile solute is added to a volatile solvent. So there are many properties of solution which are connected with the decrease of vapor pressure. So these are, the first one is the relative lowering the vapor pressure, elevation of boiling point, depression of freezing point, osmosis and osmotic pressure. See, all these properties depend on the number of solute particle irrespective of their nature relative to the total number of particles present in the solution. So such a solution, that such a properties is called colligative properties. Okay. First we will discuss here the relative lowering the vapor pressure. This. Already we learned that vapor pressure of a solvent in a solution is less than that of pure solvent. The Raoult law established that the lowering the vapor pressure depends only the concentration of the solute particles and it is independent of their identity. Okay, already we know that the equation is this: P1 is equal to X1 P0 1. So the reduction of the vapor pressure of the solvent, that is delta P1, that is change in the partial pressure. So the change in the partial pressure means P01 minus P1. So we know that is P1 is what, that is P01 minus the P1 value is, we know that P01 X1. So after getting that factorization, you will get P01 into 1 minus Chi1 or X1. That is equation 2. We know that the X2 is equal to 1 minus X1. The previous section we studied this. So here the delta P1 is equal to P01 1 minus X1 is equal to X2. So after simplifying, we'll get delta P1 is equal to what? That is P01 minus P1. So put the delta P01 minus P1 divided by the P01, because of this this going to the left side, so it will become denominator. So P01 minus P0 divided by, sorry, P01 minus P1 divided by P01. So it's, which is equal to X2, that is the mole fraction of 2. Then the P01 here, before that, that is the solution containing the several non-volatiles, the lowering vapor pressure depends the sum of the mole fraction of the solute. So this equation we can write like this. This equation we can write like this. Then see the P01 minus P1 by P01, that is the expression on the left hand side. This is the equation mentioned earlier, that is called a relating lowering the vapor pressure and is equal to the mole fraction of the solute. Okay, this is the, so this equation we can rewrite like this: P01 minus P1 divided by P01 is equal to N2 divided by N1 plus N2, or since that is X2 is equal to also N2 divided by N1 plus N2, so here the N1, N2 are the number of moles of the solvent and the solute respectively in the present solution. For a dilute solution, is N2 is very less than N1. So hence the N2 is neglected in the denominator. That is neglecting N2 in the denominator. We have P01 minus P1 divided by P01 is equal to N2 divided by N1. Or we can write P01 minus P1 divided by P01 is equal to W2 M divided by M2 into that is W2 M1. This is M1, M2 into W1. Here the W1 and W2 mass of masses and the M1 and M2 is the molar mass of the solvent and solute respectively. So here this equation from this equation known all the other quantities, the mass of the solute can be calculated. That is molar mass of the solute can be calculated. M2 we can be calculated. Then next is the elevation of boiling point. elevation of the boiling point. Already we learned that in class 11, the states of matter, the vapor pressure of liquid increase with increase of temperature. It boils at the temperature at which its vapor pressure is equal to the atmosphere pressure. For example, water boils at 373.15 Kelvin, that is 100 degree Celsius, because the temperatures vapor pressure of water is 1.013 bar, or you can write 1 atmospheric pressure. Okay, we have also learnt in the last section, that is the vapor pressure of the solvent decreases in the presence of the non-volatile solute. Okay, see, look at this picture. This is the diagram. The vapor pressure, that is the variation of the vapor pressure of the pure solvent and the solution as a function of the temperature. Okay, for example, the vapor pressure of the aqueous solution of sucrose is less than 1 bar, that is 1 atmosphere pressure, or 1.013 bar at 373.15 Kelvin. In order to make the solution boil, its vapor pressure must be increased to 1.013 bar by raising the temperature above the boiling temperature of the pure solvent, that is the water. So thus the boiling point of the solution is always higher than that of the boiling point of the pure solvent in which the solution is prepared. Look at this. This is solvent and this is the solution. This line is solvent line and this line is solution line. See, similar to the lowering of vapor pressure, the elevation of boiling point also depends the number of the solute molecules rather than their nature. So a solution of 1 mole of sucrose is 1000 gram of water boils at 373.15 Kelvin at 1 atmospheric pressure. So let T0 be, this is the T0 be the boiling point of the pure solvent, and the TB is the boiling point of the solution. So increasing the boiling point, that is the delta TB. So the delta TB is TB minus T0 B. That is known as the elevation of boiling point. See, the experiments have shown that the dilute solution, the elevation of the boiling point is directly proportional to the mole concentration of the solute in a solution. So this is delta TB is directly proportional to the M. Here the M is the molality, is the number of moles of the solute dissolved in 1 kilogram of solvent, and the constant proportionality, that is the Kb. This is the Kb. Delta Tb is the proportionality constant Kb into M. This Kb is called boiling point constant, or elevation boiling point elevation constant, or molar elevation constant, or ebullioscopic constant. See here, the unit of Kb is Kelvin, kilogram per mole. The value, usually the Kb values are given in the in numericals. So you have to find the respective like M2 or delta Tb, whatever it is. Okay. Usually the Kb value for boiling point is we will give. Then the Kf value also we will provide. See, suppose here the M, that is M is the molality, W2 is the weight of the solute, that is gram of the solute, M2 is the molar mass of the substance, W1 that is the weight of the solvent, this is weight of the solute, this is weight of the solvent, M2 is molecular mass of the solution. Then we'll have, that is W2 into M2 divided by W1 into divided by 1000. We can rewrite this 1000 into W2 divided by M2 into W1. This is equation 3. Now the delta TB is Kb and M. This is the whole value is M. So substitute this equation, that is delta TB, so Kb into M. So delta TB Kb, M is equal to what? 1000 into W2 divided by M2 into W1. So I am substituting this value here, and we can rewrite the equation for M2. Suppose we want to find out M2 means we can write like this. The M2 is equal to Kb into 1000 into W2 divided by delta Tb into W1. Okay, this is the elevation boiling point. There is a in order to determine the M2, that is the molar mass of the solute, known the mass of the solute in the known mass of the solvent is taken as a delta Tb is the determined experimentally for known solvent whose Kb value is known. Okay, so this is the formula. Next is depression of freezing point. We will see. The depression of freezing point, the lowering the vapor pressure of a solution causes the lowering the freezing point compared to the pure solvent. Look at this diagram. That is, we know that the freezing point of substance, the solid faces dynamic equilibrium with the liquid phase. So, thus the freezing point of the substance may be defined as the temperature at which the vapor pressure of the substance in its liquid phase is equal to the vapor pressure of the in a solid phase. That is, a solution will freeze when its vapor pressure equals to vapor pressure of the pure solid solvent. As look at this, this is the liquid solvent solution, this is the frozen solvent. Okay, see, according to the Raoult's law, when non-volatile solid is added to the solvent, its vapor pressure decreases, and now it would become equal to that the solid solvent at the temperature. Okay, and they lower the temperature. This freezing point of the solvent decreases. So let Tf naught, that is the T naught B, that is Tf naught, T naught F be the freezing point of the pure solvent, and the Tf is being the freezing point of the when non-volatile solute is dissolved in it. So decreasing the freezing point, so delta Tf is equal to T naught F minus Tf, this first one. Then there is the freezing point. Similar to the elevation of the boiling point, depression of freezing point for a dilute solution, for ideal, that is the ideal solution, is directly proportional to the M, that is M of the solution. Okay, delta Tf is directly proportional to M. So, or we can write it delta Tf is equal to Kf into M. Here, the proportionality constant, that is Kf, which depends on the nature of the solvent, knowing freezing point, depression constant, or that is molar depression constant or cryoscopic constant. Here also the unit is Kelvin kilogram per mole. For this is for Kf, unit for Kf. Then if look at this, if W2 gram of the solute having the molar mass M2 present in the W1 gram of solvent produce the depression in the freezing point or delta Tf of the solvent, then the molarity of the solution is given. That is, already we know that M is equal to W2 divided by M2 divided by W1 divided by 1000. So we can substitute the value in this first equation. So we will get the delta Tf is equal to Kf into W2 divided by M2 divided by W1 into W1 divided by 1000. On rearranging this equation, we will get this Kf into W2, the 1000 goes to the numerator, divided by M2 into W1. So on rearranging the equation, suppose if you find the M2 is equal to Kf into W2 and 1000 divided by delta Tf into W1. Okay. That is the determining the molar mass of the solute. We should know the quantities of the W1, W2, delta Tf along with the molar freezing point depression constant. Okay, that is the Kf. Usually the Kf value will provide you. Then the values of Kf and the Kb, which depends on the nature of solvent, can be ascertained from the following relation. That is, Kf is equal to R into M1 into T square F divided by 1000 into delta fusion enthalpy, that is enthalpy of fusion. Similarly, for boiling point, Kb is equal to R into M1 into T square B divided by 1000 into delta vaporization H. That is the enthalpy of vaporization. So here the symbol R and M1 stand for the gas constant. The R is the gas constant, M1 the molar mass of the solvent. Okay, in both cases. TF and TB is TF is a freezing point, TB is a boiling point of the pure solvent. That is in Kelvin. Okay, further that is delta fusion H and that is fusion, enthalpy of fusion, enthalpy of vaporization of the solvents are respectively. Okay.